Usually when we talk about engineering, there's this underlying expectation of physical permanence. Like, if you're building a suspension bridge, you calculate the load, you pour the concrete, the steel goes up, and
You're done.
right. At the end of the day, the engineer can just point to it and say, there it is, it's finished.
Yeah, because it's bound by the laws of physics.
Yeah.
Gravity dictates what is actually possible. The materials dictate your stress limits. And, well, there's a very comforting rigidity to that whole process. We tend to really like physical limits because they give a problem a defined edge.
But then you step into the world of software design, and suddenly gravity is entirely optional. The physical limits just disappear. We're looking at a construction landscape that is completely invisible. And honestly, that lack of physics is exactly what makes building our digital world so unbelievably difficult.
Oh, absolutely. It forces designers to essentially build castles in the sky.
Yeah.
Every wall, every foundation, every load-bearing structure, it's constructed purely out of logic and language.
And that invisible landscape is exactly where we are heading today. Welcome to the Deep Dive. Our mission today is exploring this fascinating chapter simply titled, What is Software Design?
And it's such a great topic because it's not just about coding.
Not at all. It's about the mental chess game, the psychology, and really the artistry required to design software. Because, people often assume software design is this strict, mathematical, highly predictable process of just typing away at a keyboard.
Right, like it's just pure math.
Exactly. But the source material shows it is actually incredibly elusive. It lacks absolute scientific laws, and it's driven entirely by human needs, which, as we know, are constantly evolving. And for you listening, even if you never write a single line of code, understanding this mental framework will completely change how you view complex problem solving in your own life.
Yeah, it really shifts your perspective. To understand how software is actually built, we first have to completely abandon that bridge-building metaphor.
Okay, let's unpack this, because
Right.
we need to look at why software is so notoriously difficult to plan and execute, right?
Right. And the root cause isn't that the mathematics behind it are too complex. It's because software design is fundamentally what social scientists call a wicked problem.
A wicked problem. So, it's a puzzle that actively fights back against whoever is trying to solve it.
That is a remarkably accurate way to look at it, yeah. The term actually originated with design theorist Richard Buchanan back in 1992.
Oh, wow. Okay.
Yeah, he identified a class of social system problems that are just ill-formulated. The information available is confusing, or it's, incomplete.
Because you have so many different clients and stakeholders, right?
Exactly. Decision makers who all have completely conflicting values. Like, think about a typical app. The marketing team wants it flashy. The engineering team wants it lean and fast. And the legal department wants it locked down and totally secure.
So before you've even started building anything, you're already in this massive tug of war where nobody even shares the same definition of success.
And it gets even more complicated because the ramifications of the whole system are so dense. Resolving a problem in one area actually reveals, or sometimes actively creates, an even more complex problem right beneath it.
Wow.
Yeah, one of the defining characteristics of a wicked problem is that there are no definitive formulations. You don't get definitive right or wrong solutions. You only get good, bad, or better solutions. It's heavily tied to this concept of indeterminacy.
Wait, let's clarify that term, because indeterminacy sounds a lot like saying a problem is just undetermined. Like, if I say my weekend plans are undetermined, it just means I haven't picked a restaurant yet. I just need to gather a bit more information.
The distinction there is actually crucial. If a problem is merely undetermined, it just requires more investigation.
Yeah.
You find the missing puzzle piece, and the problem becomes determinate. You solve it.
Right. You make a reservation and you're good.
Exactly. But indeterminacy implies that there are no definitive conditions or limits to the problem at all. Software design is indeterminate fundamentally because it has no special subject matter of its own. It is completely universal in scope.
Meaning the software can literally be anything doing anything for anyone.
Yes. The designers actually create the subject matter out of the problem itself. Look at the hard sciences. Things are governed by strict natural laws regardless of how we conceive them. A chemical reaction happens whether you understand it or not.
Right. It doesn't care about my opinion.
Exactly. Software, however, exists entirely because of how a designer conceives it in their mind. This subjective reality is why pioneer computer scientist Donald Knuth famously categorized computer programming not as a science, but as an art.
So building software isn't like building a bridge. It's more like trying to paint a portrait of someone who won't sit still, keeps changing their clothes, and occasionally asks you to turn the painting into a sculpture halfway through.
That's a perfect analogy.
Yeah.
And you still have to deliver a recognizable piece of art on a strict deadline.
But wait, if there are no definitive right answers and the problem is completely indeterminate, how do we ever know a program is actually finished?
Well, you don't.
You don't.
No, a solution to a wicked problem is never truly finished. Software is delivered, it goes live, but because resolving one issue inevitably unearths new complexities.
Right, those hidden problems.
Yeah, and because human needs just never stop changing, the software has to evolve continuously. We don't just build software and walk away. Its entire existence has to be managed until it is eventually retired.
Okay, so if the solution is never finished and the problem is wicked, how on earth does the tech industry ever manage to ship a product? I mean, it seems like companies would just spin in circles forever.
They often do, honestly, which is why the industry developed life cycles. If you can't cure the wickedness of the problem, you have to create psychological and organizational structures to kind of wrangle it. Historically, the first major framework for this was the waterfall process.
Which flows downwards, right? Kind of mimicking traditional manufacturing or physical engineering.
Exactly. It creates distinct, isolated phases. You have requirements, then design, then implementation, testing, and finally maintenance. You finish one phase completely before pouring your resources into the next.
So it's like a one-way water slide. Once you go down, you really can't climb back up if you realize you forgot your goggles at the top.
Right. But the glaring issue with the waterfall process is that it relies on a massive, fundamentally false psychological assumption about human nature.
Let me guess. It assumes you can gather complete, perfectly accurate requirements from the client before the design phase even begins. Like, it assumes the person sitting for the portrait actually knows what they want to wear.
Nailed it. And humans are notoriously terrible at predicting what they want until they actually see it. They suffer from I'll know it when I see it syndrome.
Oh, definitely. We've all been there.
Yeah, so by the time a waterfall project reaches the testing phase, the market has changed, the user's needs have totally shifted, and the software is basically obsolete before it even launches.
Because there's no way to climb back up the waterfall to fix it.
Exactly. So the industry had to evolve. We saw the rise of the unified process, or UP. This model is much more realistic. It features 4 phases: inception, elaboration, construction, and transition.
But how is that different from the waterfall steps?
Unlike waterfall, the workflows loop iteratively across all these phases. A major focus of the unified process is creating an executable architecture baseline very early on.
Okay, so meaning you are testing the foundation and the load-bearing walls of the house incrementally before you spend $1 million picking out the wallpaper.
Precisely. You are proving that the core structure can actually hold weight. But eventually, even the unified process felt, too heavy and bureaucratic for a lot of developers.
Which led to Agile.
Yes, the massive explosion of Agile and Scrum models. These are lightweight processes built around the absolute certainty that requirements are going to change. They rely on continuous evolutionary design and constant code refactoring.
Refactoring meaning continuously tweaking and rewriting the underlying code as you go.
Yeah, exactly. You're modifying the structure on the fly.
That's a total departure from traditional engineering. But wait, if Agile assumes requirements will constantly change and developers are just endlessly refactoring the code to meet whatever the client asked for that morning, aren't they just winging it without a real blueprint?
Well, that's the big debate. Martin Fowler, a very prominent voice in software architecture, actually sparked a huge conversation by asking, is design dead?
Is it? Are we just winging it?
What's fascinating here is that this tension is the central balancing act of modern software development. We can't just be winging it because aimless refactoring eventually turns a code base into an unmanageable knot of spaghetti code.
Right, it would just collapse.
Exactly.
Yeah.
The architecture has to strike a really delicate equilibrium. It must be stable enough to allow meaningful development to begin, so you aren't building your app on quicksand. But it must remain fluid enough to allow for structural mobility months or even years down the line.
So you tame the wickedness through rigorous requirements engineering, constantly prototyping to make sure your structure is sustainable.
That's it.
But, life cycles, whether you're looping through the unified process or sprinting in an agile framework, they're ultimately just schedules. They're external project management tools. They don't actually tell you how to invent the software.
No, they don't.
That actual creation, the heavy lifting, happens at lightning speed inside the designer's brain.
Yes, the cognitive aspect of design is where the real work actually occurs. Professionals in the field suspect that the essence of design is this rapid modeling and simulation process happening entirely in the mind.
Like running a simulation matrix in your head.
Basically, the designer is mentally proposing solutions, testing them against known constraints, and allowing them to fail safely in their imagination long before a single line of actual code is written.
That requires a tremendous amount of mental gymnastics. And the source notes that this involves bouncing between two very distinct modes of thought, right? Divergent thinking and convergent thinking.
Yeah, and the dynamic between those two modes is everything. Divergent thinking is expansive, it's generative, you are moving from concrete facts to wild, abstract possibilities.
Let's ground this in a real-world example for a second. Say I'm tasked with designing a new checkout screen for an e-commerce app. Divergent thinking is the whiteboard phase.
Exactly.
It's asking the wild questions like, what if the user doesn't have to click anything? What if they pay with a fingerprint? Or crypto? What if the checkout screen anticipates what they want before they even add it to the cart?
Right. You are exploring the absolute limits of what the software could theoretically be. It's the fun part. But you can't ship a product made of pure imagination.
Sadly, no.
So you eventually need convergent thinking. This is where you use deep reasoning to narrow down those wide-ranging choices, weigh the agonizing trade-offs, and synthesize everything into a functional architecture.
Because the reality check hits, convergent thinking forces me to realize, okay, we only have API support for standard credit cards, our server latency is way too slow for predictive card additions, and oh yeah, our budget runs out in 3 weeks.
Exactly. Bridging those two modes, the beautiful, limitless idea and the painful, restrictive reality, involves traversing what researchers call cognitive distance.
Cognitive distance.
Yeah, that is the gap between the grand concept in the mind and what is actually realizable when forced into an implementation medium, like actual code. Your mind conceptualizes a flawless instant data retrieval system, but convergent thinking forces you to reconcile that with physical memory usage and specific programming syntaxes.
Here's where it gets really interesting, because this sounds identical to the creative process of writing a novel. You have this sweeping, epic story in your head, but then you have to sit down and figure out how to convey it using only 26 letters and some punctuation.
It's a very similar struggle.
But how do software designers avoid losing the big picture when they are forced to dive so deeply into the weeds of syntax and server limits?
If we connect this to the bigger picture, the hallmark of a truly great designer is what's known as systems thinking. They don't just stay in the clouds brainstorming, and they don't just stay down in the weeds typing code.
They bounce back and forth.
Continuously. They loop between the abstract concepts and the concrete realization. It demands an incredible tolerance for ambiguity. You have to comfortably hold a massive, complex, half-finished puzzle in your working memory, constantly adjusting your focus to ensure the final architecture actually serves the human need you set out to solve.
But having a perfect synthesized vision in your head doesn't build a product, though. You have to somehow extract that vision from your mind and share it with a team of maybe 100 other people. Software design isn't just about thinking. It is fundamentally an exercise in translation and communication.
Right, because software is primarily read by humans, not just machines. It is written once, but stakeholders, managers, and future developers need to read and understand it over and over again. And because the construction landscape is invisible, designers have to invent ways to visualize it.
Which brings us to tools like UML, right? The Unified Modeling Language.
Very good.
They are essentially drawing maps of an invisible city.
We call them architectural views. And one view is never enough because different people interacting with the software need completely different sets of information. So designers create customized perspectives.
Like what?
Well, you might have a logic view showing how the abstract elements interact, a process view detailing how it communicates with external hardware, or a layered view displaying the hierarchy of the code modules.
The source material also mentions creating view packets, which are highly targeted for specific stakeholders. This makes a lot of sense. It's like using a map app on your phone.
How so?
Well, if you are the database administrator, you get the highly detailed, down-in-the-weeds traffic view because you need to know exactly where the data bottlenecks are happening. But if you are the CEO, you just get the zoomed-out country view. You don't care about the stoplights. You just need to know the major cities are connected.
That's a great way to put it. And we also communicate design through the very frameworks we choose to build with. Our sources highlight the React framework, originally developed by Facebook, as a prime example of this.
Okay, React.
Yeah, React uses what is called the declarative paradigm. utilizing specific syntaxes like JSX and a mechanism called a virtual DOM. By choosing React, a designer is actively communicating to other developers how the system's user interface is meant to be reasoned about.
Let's break down that declarative paradigm because that sounds like heavy jargon. In traditional programming, imperative programming, you have to give the computer step-by-step directions.
Right.
It's like telling a friend, drive 400 feet, turn left, stop at the sign, turn right. But a declarative paradigm is more like giving your friend an address and letting their GPS figure out the route. You tell the system what you want the screen to look like, and the framework figures out how to render it.
Yes. And that ties directly into the virtual DOM you mentioned.
Hmm.
Instead of carrying down the entire web page and rebuilding it from scratch every time a user clicks a button, the virtual DOM acts like a rough draft.
Okay, so it just compares the versions.
Exactly. The framework compares the rough draft to the live web page, identifies the exact single word or button that changed, and only updates that one specific piece. It is a highly efficient way of communicating state changes.
But this brings up a huge debate in the software world. If the code itself dictates so much of the design, and frameworks like React are doing the heavy lifting of communicating how things work, why do we need the map app at all?
The code is design argument.
Yeah, Jack W. Reeves championed this. He basically argued that diagrams and architectural views become obsolete the absolute second the actual code changes. So if Reeves is right and diagrams go out of date immediately, why spend time and money documenting the design with all these elaborate views?
It is a constant point of friction in development teams. The reality is, documenting the design isn't really about providing a perfect, flawless technical manual for the coders. It is about risk mitigation.
Risk mitigation for the business side.
Exactly. It is about securing administrative support, getting budget approvals, and making sure the business side and the technical side are totally aligned early on in the process.
Got it. So you don't map out the placement of every single nail in the house. You just get everyone to agree on where the bedrooms are before you start pouring concrete.
To avoid the pitfall of obsolete diagrams, smart designers use a specific strategy. They exclude the low-level modules from the documentation entirely because those change daily. Instead, they focus the documentation on early, high-level communication to validate the core requirements with the stakeholders.
Right, before the incredibly expensive coding phase kicks into high gear.
Exactly.
Okay, so we are talking about using React frameworks, standardized architectural views, mitigating risk by communicating with stakeholders. If we are increasingly relying on these strict, pre-built frameworks and standardized ways of communicating, it begs the question, are we finally moving away from the art of software design and getting closer to a strict, predictable science?
The industry is certainly inching toward what is called design formalism. Today's software isn't built to be retired in a year. It's built to last, scale, and evolve. So we are seeing a shift toward paradigm-neutral design.
Meaning you aren't locked into just one way of thinking.
Exactly. You use whatever method works best for the specific module you are building. And developers are increasingly utilizing formal ingredients, things like APIs and microservices.
APIs are essentially digital waiters. They take a standard request from one program, carry it to another program, and bring the response back. They are standardized plugs. So we aren't building everything from scratch anymore. We are assembling pre-made digital blocks.
Yes. And Barbara Liskov, a Turing Award-winning computer scientist, drew a fascinating comparison regarding this shift. She likened software design to constructing mathematical proofs.
Mathematical proofs? How so?
When a mathematician proves a complex theorem, they don't solve it all in one massive leap. They invent lemmas, intermediate, smaller steps. They decompose the grand problem into highly specific subproblems.
Okay, so in software, that would be breaking the massive application down into highly specific data types and discrete operations.
Exactly. You organize and refine the abstraction over and over again until it perfectly meets the reality of the machine. Ultimately, computing is just a sequence of information representations. It is a series of statewise transformations from raw bits and bytes at the bottom all the way up to the complex user interfaces we interact with.
So what does this all mean? If we are breaking things down into strict data types and using formal ingredients like APIs to assemble programs step by step, I have to challenge the math analogy here.
Go for it.
In mathematics, a proof is a universal truth. General logic dictates that if the steps are correct, the conclusion is undeniably true. But we established right at the beginning that software is a wicked problem. It has no definitive right answers. So if we have all these formal mathematical ingredients, will we eventually unlock a formula for perfect software?
This raises an important question, but the crucial difference lies in how success is measured. A mathematical proof is shown to be true by general, universal logic on a piece of paper. A software design, however, is only proven to work by implementation and testing in the messy, unpredictable real world.
Because it inevitably involves human beings.
Exactly. You can take the most formal, logical, scientifically pristine ingredients, the APIs, the frameworks, the bits, the bytes, but you are embedding them into an informal, deeply human structure to solve a constantly shifting human problem.
So it's still an art.
Yes. As long as software remains tethered to human needs, that process of synthesizing the pieces together elegantly will remain firmly in the realm of art.
It will always be the painting of the moving subject.
Precisely.
And that brings us to the core value of this entire deep dive for you, the listener. Software design isn't just a technical manual for programmers. It is a profound lens for viewing the world. Recognizing that most modern problems in business, project management, and life are wicked, that they don't have perfect right or wrong answers, only better or worse ones.
It's about learning to tolerate that ambiguity, you know?
Exactly. Practicing the mental gymnastics of cycling between divergent, wild brainstorming and convergent, painful decision-making. Those are skills that will make you a sharper, more resilient thinker, no matter what profession you are in.
It provides a necessary mental framework for navigating a chaotic world where the requirements are just always changing.
But before we wrap up, we want to leave you with one final provocative thought to mull over. We've spent this time establishing that software design is deeply human. It is a wicked problem full of shifting desires, communication gaps, and artistic intuition. But as we enter an era where artificial intelligence can instantly write blocks of code and assemble these formal ingredients faster than a human ever could, we have to wonder, will AI eventually figure out how to tame the wickedness of human needs better than we can?
Or will our demands, our shifting requirements, simply get endlessly more complicated to outpace the machines?
Something to think about the next time you update an app on your phone and wonder what exactly changed beneath the invisible surface.